The wave nature of electrons is suggested by experiments on electron diffraction. Okay, so this is simply just bookwork. So let me just explain, right, the electron diffraction experiment. So we know that by the de Broglie equation, right, lambda equals to h over p. It tells you, de Broglie equation, right, gives you a way to figure out what's the wavelength for a typical particle, okay, that has a momentum p. Okay, so here, right, we have the electrons being fired out, okay, and we accelerate them with a certain voltage, okay, so they will have a certain Ke, and the energy will be VACC, okay. So with this particular energy, right, there will be a corresponding momentum, because K is equals to P squared upon 2m. Okay, so you can see, right, the larger the potential difference you use to accelerate the electron, the larger its momentum, hence the smaller the wavelength. Okay, so these electrons hit the graphite screen. So what is the graphite supposed to do? This graphite, right, is to serve as a diffraction grating. Yeah. How do you think about this? Because, right, you see, the graphite, right, is made out of structured layers and layers of atoms. Yeah. So there are gaps between the atoms, okay, which is like the electron cloud, right? So you see most of the atom is actually empty. There's some electron cloud. So you can think about the gap between atoms, right, as like the slits. So the electrons, right, can go through all these slits, all these openings, and reach the other side. Okay, so this regular spacing of the graphite material is like a regularly spaced slits. So it's like a diffraction grating. Moreover, right, you have many layers of graphite. You know this from your chemistry or maybe secondary school science. So many layers of graphite, right, is like many diffraction grating put back to back. Normally, right, when we have just a simple diffraction grating, which is like slits which are vertical, the light go in. When you see on the screen, you see the zeroth order, first order, second order, so on. They appear linear. But let's say, right, you have multiple diffraction grating. The first one is this orientation, the second one is a bit slanted, the third one is yet more slanted, so on. So you have many of them. So when you look at the screen, right, you will have the center still there, but you see your first order, right, will be the first order of all the various orientation. Second order also, second order for all the various orientation of the slits. So that's what the graphite here is achieving. Okay, it's like many layers of diffraction grating randomly ordered. So end up, right, we see that the electrons reach the screen, we observe them, we see rings instead of the bright fringes. We see bright rings. Yeah, so that's the origin. And you can see, right, on this diagram here, high and low voltage, right? See, when you have a high voltage means what? Low Ke, or means, right, low momentum, hence means large lambda, okay, and vice versa. So the diffraction grating experiment, right, d sine theta equals to n lambda. The larger the lambda, the further the bright fringe. Yeah, so if this is a bright ring, then it simply means, right, the larger the radius of the ring. Okay, so that's how you explain the different observation. And finally, right, why are you able to see the rings? It's because, right, this screen is coated with those kind of sort of glow in the dark material, but it's actually, right, called a phosphorus. Actually, I'm not too sure how to spell it. Okay, phosphorus fluorescent material. So it's some material, right, that will glow and give out light when electron hits it. So we can't see electrons, but we can see the positions where electrons land on because they give out light. So we indirectly observe the electrons.